Hi everyone, this is James. I'm the lead developer at Stealth R&D. Stealth R&D is a company that supports and develops on the blockchain of the cryptocurrency known as Stealth. Stealth was launched in 2014. It was fairly mined by the standards of the day for a few weeks and then switched over to proof of stake. It's been proof of stake ever since then. The blockchain is over 3 million blocks long. It's listed on several exchanges, including Bitrex and Whitebit. And at Stealth R&D, recently we've been working on protocol improvements, the most significant of which is called Junaeth. Junaeth is formerly known as quantum proof of stake. It is a highly economic system that is a protocol for scalable, fast blockchain. And I've written about it in blog posts and the white paper, and I direct you here. I should have had this up front, but I'm making this video kind of real time here. This is our website, stealth.org, and you can see it's down here in the marquee, stealth.org. You can go to stealth.org and learn about the coin and what we're doing with what formerly was known as quantum proof of stake is now known as Junaeth and will be reflected as such in our new website that is, you can see, has not been published yet. It's described here in briefly, and if you go to, say, our white paper, it's discussed there. One thing you can do is come to our news section and scroll through. Last week, February 22, so that's going on a couple of weeks now. I had a blog post and a video where I describe the functionality of something we're working on called the StealthExplore API. The StealthExplore API is an application programming interface where you can send commands from one computer to another using a program or commands you type in, although that's used less frequently than using a computer. You can send these commands and get information about the blockchain back, and it comes very fast, and it is basically derivative information from the blockchain. So how many addresses are there with above a certain amount of coins, or how many how many transactions does a particular coin have, or give me those transactions. These are the kind of things that are important for a true coin infrastructure. For example, for block explorers, where somebody goes to a website and they get information about the chain. I don't know, everybody's probably used a block explorer before. And for light wallets, different types of light wallets. And so you can have a light wallet that's an app, or in the browser, where an individual has on their own computer storage, backed up hopefully using Time Machine or something like that, their own keys, and so those keys never leave their device, like their smartphone or their desktop, and they can use a light wallet and interact with the blockchain. That type of thing requires an API. Typically, this is achieved having a client running on one side, on say a machine, and a block explorer querying the client each block that it comes in, or the blocks are pushed to the block explorer, and the block explorer digests all that information, stores it in a server query language database. It's a good system, and it's been efficient enough, but at Stealth we kind of we just push the limits. We like to see, we like to take the technology, the programming technology, like the language you're using or the libraries you're using, and push them all the way and kind of think in terms of the computer science, how you're achieving this, and just go ahead and make it efficient up front. This, in some circles, this might be known as premature optimization. But and typically I believe in the type of development that doesn't do premature optimization, but in blockchain, it's a decentralized system that needs to scale up to global use. So uh, if you don't premature optimize, you're basically going to run into problems sooner than you would if you try to be optimized in every way you can going forward. So you just have to think about every design decision and optimize those. And so that's what we've done with the blockchain. At least the augmentation, the code augmentation we've done onto the code base that we were using. All that is efficient as I could conceive of it. We may find more ways to make it efficient in the future, of course. We're always looking for ways to make it more efficient. It has to scale to global usage. Here I'm doing that with the API. I'm making every single design decision around what is the most optimum and efficient way to do it. And if somebody has some philosophy about premature optimization, they can go write a blog post about it and make themselves feel better. And they can write a nice critique about how we're doing optimization here, but we're going to do it up front and we're going to be ready. So what have we done? Well, last week in this blog post, it happens to be up on the screen. I have a video where I talked about the API and the various commands that API already has in it. I was just reorganizing the window there so I could see it a little bit better. I'm on my laptop, so the screen is very small, and I don't have a second monitor hooked up to it anymore. So last week, what I had done is or a couple weeks ago now, what I had done is I completed kind of what I would consider the prototype for the implementation for the API. The API will probably not change very much, but the implementation will. Meaning I'm very aggressively looking for ways to make it more efficient. I went through a few commands. One command I did was I found an address that I can't remember what the address is exactly, but that's okay. And that address had 1,500 outputs. As I mentioned in the last video, an output is money going into an account. It's a counterintuitive name, but just try to remember an output is money going into an account. And this account had 1,500 or 1,511, if I can remember correctly. And it took about 1.5, maybe 2 seconds. So we can watch the video and get a stopwatch and see exactly how long it took to pull up those 1,500. And I just felt like I was losing some time there. I wasn't quite sure. I kind of tracked it down, and I realized that the time was lost to first accessing a database read, then accessing a flat file blockchain read. So blockchain data in the way this is set up in these Bitcoin type these clients that are these blockchains that started a long time ago with the Bitcoin code base and still uses that file format. The blockchain is stored as a flat file. It gets a new block, whether it's orphaned or not, it just appends it to the end of the flat file. And so there's indices, transaction indices, that has this information where that transaction is located in the flat file. It's a pretty interesting setup, actually. So what I think I was losing some time on was I would access the database, get the transactional information, which was the money going into the account, the output, then going and looking up the index information. So transactional information, looking up the index information, and then going and doing a read on the flat file and reading more data than I needed to in order to get the information that would be necessary, say, for a light wallet. And so I decided what I was going to do is go ahead and store more data in the key value database we're using. And I went into key value databases in previous blog posts and a little bit in the last video. These are highly optimized. I won't go into that today. What I want to do today is set everything up like I had in the last video. I've synced, like in the last one I synced 1.3 million blocks, and then I was syncing the blockchain live from the network. I'm going to do that here again today. This time it got up to 1.4 million from a bootstrap, and I killed it, and now I'm getting it to sync from the network. So it's syncing like a block every couple of seconds or something from the network. My connection is a little faster here than it was where I was. I was traveling and now I'm back. That's why I was using my laptop, but I want to reproduce everything. So that means blocks are probably getting retrieved from the network a little bit faster, so my computer's probably got a little bit more of a load on it, especially on this client. That might impact the speed. It's still reading and writing to disk. It's validating signatures. It's doing everything it was. It's encoding this video because I'm shooting it on my laptop. And when I type commands, I'm going to type commands, and there might be a little bit of monitor shake, but I guess we're just going to have to live with it, okay? This is a demo of the API, not a professional video, blog series or anything. It's not monetized. So bear with the shaking. And let's kind of see if I can do this. Here's a video. So the block count, let's see if this works. It was locking up there. Okay, so look at that. That was to get the block count, which is super simple operation. It took about like a quarter second. Okay, so just to get one number, it took a quarter of a second. So last time I found an address with about, I think it was 1,511 outputs. I couldn't remember. I didn't watch the video and type down that, and I didn't make a note where I could copy paste the address. But we have basically the pre-mine address. If I can bring that up, because I know I typed that command. The pre-mine address. There's a pre-mine address. That address is empty. I wrote a whole blog post about the pre-mine. It's in the news section if you want to scroll down to it. In this one, what I'm going to do is use this one, and I'm going to get 1,600 transactions from it. Okay, so this is get address info. That was faster than get block count. Let's see if get block count sped up. See, look at that. Just to retrieve the block. I don't know who wrote that. That wasn't me. Look at that. Get block count. Quarter second. Get all the information about this address a little bit faster. It was a lot faster the first time. There's some variability because if you check it out, it's syncing blocks and a little bit faster because my internet connection is faster here. It's going to be slow because there's some slowness to the synchronization that needs to be improved. I'm going to be working on that very soon. But we had these infrastructure requirements, so we got to get out. And we decided I'm going to build an API into the client that can satisfy these requirements. They're going to be the reference API. You fire up a client, you enable it as I showed in last week's in the blog post, the video. You can enable the API at boot. It'll index it for the API, and then everybody can have the same API. All I have to do is run a client. There's no separate database running SQL, can be less efficient if you're not doing it. It leaves a lot more memory, and they have problems like that. And as opposed to this, which is a very low level key value database, very highly optimized. Some would say prematurely optimized, but they can pontificate about that if they want. So this address. The reason it goes slower and faster is there's different loads on the computer because of syncing the blockchain. So we're going to have to build that in. And you want to do what you want to do is you want to minimize disk reads. So that's what I try to do. This one, if you notice, so it doesn't have 1,511 outputs or so. It has 32,154. A lot more. 20, almost 20 times more. Almost 20 times more. And those are all staking transactions, but it doesn't matter the type of transactions. It's going to require, each transaction is the same size in the database records on the disk drive, so you have the same access, read, write times. It doesn't matter the type of transaction. So let's see what happens. One thing about these is I don't know. I don't know if this is going to be good or bad, if this is going to be faster to get 1,500 transactions or 1,600. So the command is get address outputs, and I even added more information. Yes, I added more information per output in this one than I did last week. And I'm going to do 1,600. Y'all ready? 1,000. Oh, I didn't tell it. Okay, I didn't do the command correctly. I wanted to get outputs 1. I'm sorry, that was 1. I was like, it's empty. Okay, that was a huge fail. I didn't type the command correctly. It went 1,600 to 100. So obviously I should say, give it an error. So it's saying, oh, I got to tell it what address. No wonder. This address, it should, this is the magic of not testing before you do this. Okay, I didn't give it an address. So the first one, the address, it thought it was 1,600. It should have said that address was not valid, so I'll have to figure out why I didn't do that. Same with the second time I ran with just, this is the proper command. Okay, did we count that up? We can go back and look at the video. I think that was about a little less than a second. So 4 seconds to get 1,511 last time. Okay, now they're cached, so they should be much faster this time. Okay, let's just now compare. So I'd say that was a success. So the second time I just ran that command, you can't count that because that information was cached in RAM. So it's just going to spit those out. It was the first time, and the first time could just be crazy, but I think it was about 0.9 seconds. We can time it. We can put a stopwatch to it, see how good my sense of time is. Okay, so less than a second. I'm going to say it was less than a second. Last time was clearly like 2 seconds. So that's an improvement. I can live with that. Now, we can actually, so it hasn't cached the rest of these, so we can actually go like 1601 to 3200 and see 1,000. Oh, I gotta put the address in, guys. If you don't give it an address, it should really issue an error. Okay, noted. 1,000, 2, 1,000, 3, 1,000. Okay. You know, I think it did pretty good. If you do that again, it's like instant. Should be instant. Okay, let's try it again. 3201. I'm gonna do it like this, so I don't do that thing where I get a null set anymore. To what would it be? 4,800. 1,000, 2, 1,000. Yeah, so less than 2 seconds. We'll have to go back to that video and see. It could have been a lot longer, but that seemed like it was faster. That's about as fast as I can make it. On a real client, you'll be able to there'll be settings where you can. I've already thought about this, where you can limit the number that you request. Like if you request 100. And I really don't know how much of this latency has to do with the fact that that it's syncing blocks, like it's syncing a couple of blocks a second there, I think. And that's just and that's heavy duty taxing as well as encoding this video. So I just don't really know how much of this is like disk latency that you can't do anything about, that's not going to be happening on a regular client. I mean, if I wanted to, I could have. One way to optimize this in the future is you can actually set the database directory. Already you can do this, I'm pretty sure. Let me think. Maybe not. I think, but I will be able. I will do it. You can set the database direct. You'll be able to set the database directory. This is not really This is not really hard to do on a different drive, so that any read and writes on your main drive, say where your blockchain flat file is, say it's recording blockchain and all that, is not going to influence the API drive. Although there are a lot of read writes to the actual database directory that this is using anyway, so we may not be able to do anything about those latency, but a fully synced client will not have that latency. Okay, so now I have to remind myself what the next thing I was going to do. Oh yes. Okay, what I wanted to do here is let's see. So we have all of them. We have 32,000. Okay. Let's just do this. 1 to a big number, and I'm just going to funnel it into a file I call a race. When this returns from this command, the whole file will be written, and it will have spit all those out into the file. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000, 7, 1,000, 8, 1,000, 9, 1,000, 10, 1,000, 11, 1,000, 12, 1,000, 13. Okay, 12 seconds, 13 seconds. We'll say it was 13 seconds. Okay, so yeah, I was on 13 whenever it stopped. So to get 32,000 outputs took about 13 seconds. That's interesting. So let's see how much data it wrote at that time. I think you have to do ls minus k. Yeah, so 14 megabytes of text data that it collected, formatted, and wrote to that file. So in 13 seconds, so 1 megabyte per second. We can think about if that's too long. I think this is about as, I can't fathom how I could improve this at this point, because all the database, all the information that went into this file called erase, here it is. These are all the transactions. All that information is in the key value database. So I can look at it and see if I can get that to go faster using some kind of batch read, like where it reads every record into RAM, then it parses those, you know, and then it fills data structures, and then it creates the JSON. But it had to create all this JSON too, and that may be an expensive process. I don't know if I didn't really optimize that, but I think that's pretty well optimized already if I had, just from what I know from the code. But here we go. So there's a, here's the information you get for each output. You get the transaction ID, the index in the transaction of that output. So each transaction has inputs and outputs. Outputs are money going into an address. Inputs are money going out of an address. So it's backwards from what you would think intuitively. And each transaction can have multiple of those. V out is, you know, blockchain API speak for the index for which one. So it can have 100 and 10 both going into an address. Those would be outputs. The 100 would have index 0, so its V out would be 0. The 10 would have index 1, so its V out would be called 1. Okay. How much that amount was for? Okay, well, this is clearly staking transaction. What the block was in, how many confirmations it was, where the block time was. I don't have the height here. Height is actually part of this record, but instead I have confirmations. I should have height and confirmations. That's not a big deal. I'll watch this video and try to remember to put that in. You need a height on that just so people can see it. The block time, that can be translated 140501, 140555. That's a cool number. Whether or not it has been spent. Okay, so this output has been spent, and it was spent in this transaction as an input. Remember, inputs are money going out. Input index 0. So the next so it was spent here in this transaction. So everything you would kind of need in a light wallet or an Explorer, except height, which I guess I just need to put in. That's going to take about 2 seconds. If you want to do a full report on this transaction, if somebody really wanted to see how their money flow is going in a light wallet or an Explorer, then these are going to have all. It's the same with the inputs too. We can just look at an input real quick. So instead of this crazy thing, just get the first 2 and inputs. We're done with the performance testing. Was it awesome? Did it do a little better? I think so. I think my efforts were worth it. Okay, so that came back very quickly. On an input, you get kind of some analogous information: which transaction, what the index was, the block hash for that transaction, how many confirmations. The height is part of the record, but I need to put that in the output here. What the time of the block was. Interesting enough, this was staking transaction, so it all happened in the input and the output were all part of the same block. That's why they had the same time, 140501, 4055, and then this points, the input points back to the output that's spent. So the inputs and outputs are matched. The input follows the output, and the input that follows the output is matched to the preceding one. The input is not matched to the next output, because the idea is the inputs can be mixed into different outputs. So it's not symmetric. From output to input is not symmetric with input to output in that temporal order. If that makes any sense. Let's see. So, yeah, I think that's pretty much it for today's. What would really be cool is a video blog about the drama going on with Steam. And why would I even bring that up? Let me tell you. So, believe it or not, one of the my first experience with delegated proof of stake was with Steam. And if you go, I can actually Google this. I think I put this was in a video, Steam James Stroud review. Come on, man. Short review is, yeah, there I am. Okay, my name's in print. I'm famous. So here I was one of the first, 4 years ago, I was one of the first people to stumble on Steam, as a as a blogger. And I, at the time, I really could see the value in it. I think this might be just after it was on Bitrex. It had some cool features that I talk about in this review. One of the real cool things was that it was mined to begin with. I like that part. I like the way the mining went. It was a little different. I write about it in here. It's been a long time since I read my review, but one thing I came to find out was it worked on something called delegated proof of stake. And delegated proof of stake is where everybody who owns some Steam, in the Steam system, there's different models here. They're all very similar. There's Steam, there's whatever they're doing in EOS. They have a very similar structure to Steam. This was kind of the precursor blockchain to EOS. There's BitShares, which was kind of the precursor blockchain code base to Steam. Then there's this whole family that is related to Lisk. I believe Lisk I believe started as a coin called Crypti. And these have a different, these all kind of work the same way. And delegated proof of stake has really, a lot of high performance blockchains use it. The reason is because you know who's going to sign the next block. And so you can schedule the blocks. This I thought was very interesting. You can schedule the blocks, but it's delegated, okay? And it's delegated in a proof of stake coin. And all of these coins like Lisk, BitShares, and EOS, they were all pre-mined. Not like Stealth had like this little pre-mine that has long since been spent on development. These are fully pre-mined. With Steam being an exception where it was mined out, but most of that mining, like the vast majority of that mining, was done by the Steemit company. For those of you who've been following, Steemit, the company had a lot of shares, had a lot of Steem, the coin vested, and that vested is a vesting process where you lock it up on the blockchain. That allows you to vote for block signers, and there's 20 main block signers and an alternate every round, and it's scheduled, so it could be the block signer 10, then block signer 1, then block signer 5, then block signer 2, like that. All of them are arranged in a cycle each time, and then they all sign a block, which is a pretty good system because you know who's signing the next block. You know there's no competition for the next block, and competition is inefficient. The way to think about things is think about the extremes. What's the most extreme competition there is? Football? No. War. War is the most extreme competition, right? People are getting slaughtered in war. It's bad. But think about how inefficient war is. I mean, it's great for economies. You build a lot of tanks, buy tanks, you sell tanks, tank guys get rich. The banks are loaning money. Great for economies. But actually, those resources would be better spent, say, on infrastructure, if you want to improve the quality of life. And one real hindrance, one real drag on quality of life is, say, getting shot by a bullet in war. It reduces your quality of life. So from a quality of life perspective, this level of competition is inefficient. Okay, from an economic perspective, it actually is inefficient in terms of a resource usage perspective. From economic perspective, it's probably pretty good from economy competition. It's interesting. Competition has a stimulating effect on the economy. Um, it's actually kind of interesting to think about because Bitcoin, right? Bitcoin is the most competitive. It's an arms race. It's literally an arms race of mining equipment, and I mean, it is the belief of a lot of Bitcoin proponents and maximalists. They draw a distinction between those two. That this competition and the resource inefficiency of that actually stimulates the Bitcoin economy, and that's why it has a tremendously high market cap relative to any other cryptocurrency. And from a theoretical standpoint, I don't know if there's any way to make sense of that, but if you draw parallels between that and say other forms of competition, it's consistent. It's consistent with war being a stimulator of economies. It's consistent with the most competitive and brutal sports being the ones that have the most revenues. I mean, it's consistent with notions of evolution, where the most competitive members of the population are the ones who reproduce. So competition is stimulating. However, it's inefficient. And one problem Bitcoin does have is it is not efficient enough for global use at this moment. You know, when Bitcoin price starts going up, the Google hits start going up, the transactions slow to a crawl. Sometimes you can't get a transaction through. Sometimes it doesn't matter what kind of fee you put in there. Well, that may matter, but you're going to have a high fee to get a transaction through. Not 50 cents, which is considered a high Bitcoin fee, but $5, $10, $20 may not get a transaction through. If you really want it through, you might really pay a premium when Bitcoin is skyrocketing. So that level of inefficiency, I don't think they've solved that puzzle yet. To have that level of competition but still have efficiency. So this may be an insoluble conundrum. We'll see. Delegated proof of stake addresses this problem. It gets rid of competition at the level of choosing the immediate next block signer. It has scheduled blocks. The competition in delegated proof of stake is ostensibly that the block signer is more trustworthy, a better contributor to the blockchain ecosystem. Maybe they're writing code, maybe they're writing infrastructure. But the problem with delegated proof of stake typically is that acquisition by the central stakeholders, by the main stakeholders, is not typically a fair process. Fairness is a scale. It's hard to achieve perfect fairness, like it's hard to achieve perfect efficiency. In thermodynamics, it's hard to achieve justice, perfect justice, but it's a sliding scale of fairness. And most of them are just unfair. Even Steam was mined out, which is one of the things that I thought was really great about the blockchain at the time. There has been tremendous criticism about the fairness of the original mining process, and it's been called a ninja mine. They were mining it fast and maybe not presenting the realities of the intended use. And some people argue, well, it's fine. Others say that's just horrible. But what happened is you get all this stake that was centralized to the Steemit company, which did a tremendous job building Steam into the coin it is and supporting it with the infrastructure namely steamit.com that my browser is on right now. And they had a lot of stake, and one of the sort of implicit promises, I don't know if it was ever explicit, was that Steemit would never vote for witnesses. Okay, Steemit decided the people who started it, the founders of the Steemit company, would sell the company and the stake. That was the real value in the company, actually, the coins. Coins were worth a lot of money, you know, on the market. You probably couldn't sell them all at once without crashing the market, but if you could find a buyer like they did, of course, the amount they sold it was not disclosed, and it was sold to Justin Sun, who is either the lead developer, the founder of Tron. I'm not into Tron, so I don't really know what his role is there, but he's like the main guy for Tron. Main guy, Tron main guy. And I don't really understand what happened, but the Steam witnesses who had been elected by the community, and a lot of that community were also stakeholders who got in on the Ninja mine. I don't know how much they have left. And so by now the distribution might be such that the witnesses, these are the block validators, the 20 top block validators are considered as, collectively known as the witnesses. For some reason, the witnesses decided I could be mischaracterizing this, and if I am, I apologize. My apologies to especially the witnesses. The witnesses supported or released a fork of the chain that temporarily locked the stake that was Ninja mined. I'm using that term because others have used it. That was Ninja mined by the Steemit Corporation, and they locked those funds. For what reason, I don't quite understand. So I can't say whether it was good or bad, okay? But the fact that they could collectively do it, to me, what they did, I can't assess. And even if I had an opinion, I probably wouldn't give it because it's probably biased or flawed in some way. But the fact that they could do it, to me, represents a big problem with delegated proof of stake. That the 20 witnesses could actually collude to deprive stakeholders, whether you think the stake is legitimate or not, is just kind of mind-boggling. And collude could be just a horribly biased term. I didn't really mean to use it, but let's just use it for now. They could collude to lock the Steemit Corporation out of their access to their funds. That's to me, if anything epitomizes the problem with delegated proof of stake, it would be this potential. Okay, what could be worse than that? What could epitomize the problems with delegated proof of stake more than witnesses locking Tron out of their stake? Tron then, maybe I have to avoid the word colluded. It's such a loaded word. Organized, coordinated with exchanges to use deposits to vest those irreversibly, but it takes like 13 weeks to divest these. user funds, their users, people who deposited their coins, who are expecting those coins to be liquid in case there's a run on an exchange. They used those, they vested them, now they're frozen for an amount of time, and elected their own block signers, witnesses, in order to reverse that fork where they were locked out of their own stake. My friends, ladies and gentlemen, fellow Americans and citizens of the planet Earth, seriously, this is proof of stake. It's flawed. This cannot, to me, this cannot be a reality in blockchain. So it's surreal. It's absolutely surreal. How does this relate to stealth? You're like, what is the point, man? Here's the point. In stealth, I decided a long time ago, that these types of things were possible in delegated proof of stake for a number of reasons, because you have a pre-mine, you're going to have a ninja mine in order to control that blockchain. The theory is to control the blockchain and get the blockchain off the ground. It's proof of stake. In proof of stake, you can have a pre-mine because you never need a proof of work. And for Steemit, the model was to have a ninja mine up front. There were posts by the founders that outlined this strategy even before they ninja mined it. But the block scheduling is beautiful. You get the competition over with. And vesting is actually interesting. Vesting, all proof of stake has a time component, has a vesting component. Every bit of proof of stake that's been invented has a vesting component, with the exception of the nano model. But we'll think about that, maybe have a talk about that one day. Where your coins have to be locked up for a certain amount of time before you can vote for a block signing representative. Nano doesn't have this model, strangely enough, and we have to think about the security of that system, but it has been secure so far, so I guess it works. And I don't think it's the same kind of proof of stake. I don't think the model is exactly analogous. So we may have to put Nano out of our heads in this comparison. But in delegated proof of stake, you have this vesting component that even Tron had to do, and Tron is talking about electing witnesses by brute force, using user funds at exchanges in order to have a quick vesting reversal, in order to circumvent the rules completely. It's crazy. But with Junaeth, or quantum proof of stake as it was formerly known, in Stealth, I like the block scheduling. I like the vesting. But what's the ultimate way to vest? What's the ultimate in vesting? I like to take things to extremes and see if they make sense. What's the extreme? Forever. You vest forever. You buy a token that cannot be liquidated except through a market. You can sell your token. You got to be transferable. Assets have to be transferable. It's like a fundamental property of property. And you have to be able to sell it, but it can't be liquidated it can't be converted on the blockchain back to Steem. You can't erase one and get all your money back. It's a permanent vesting, and that asset has a reputation that grows, and whoever owns it needs to tend to that asset. So the asset has a life of its own. It's a people too. It's a corporations or people too. You can think of it as a little incorporated element on the blockchain. It has a life of its own. People need to nurture it. If it gets transferred, the new owner needs to nurture it, or they're going to be losing money. They're going to be wasting their money. And in my model of the economic universe, people are making decisions based on their bottom line. You know, some people do it better than others, but typically, when it boils down to it, people are looking at their bottom line. They're doing it for the money, and you want to harness this uh, this behavior that people have to just look for their bottom line above anything else, above any sort of code of conduct you could hope to impose on people. They're going to be looking for their bottom line. So you want to use that behavior as one of the primary mechanisms of blockchain security. So each stealth node that you purchase as a token has a reputation that goes along with it. People have to manage that reputation. That reputation is improves with every block you sign, and degrades with every block you fail to sign in the schedule. And there's no going back, and there's no soliciting a vote from somebody. There's no being friends with the person who ninja mined or got the pre-mine, founded the coin, and getting in on the top slots. There's no being that person and pretending to be somebody else and running a top slot and exploiting it, and even exploiting it to lock somebody out of funds or to prevent some community decision. There's none of that, where one entity is the de facto community because they ninja mined or pre-mined all the coins or bought that stake from the market. This Tron thing is probably one of the most interesting things to happen in blockchain, in my opinion. In the drama category, up there with the DAO. Remember the DAO was the Ethereum coin that was an ICO that somebody figured out how to drain all the DAO funds. That was hugely dramatic. This one is far more complex than that. Looks at many more issues related to blockchain and delegated proof of stake. What does it mean to have a secure blockchain? What does it mean to have a fair blockchain? It's amazing. So I've spoken about that. I've rambled on. I was going to save that for another post, but I couldn't help myself. You've watched this far. Congratulations. Hopefully I gave you something to think about. And I'm going to release my latest revisions to the code base, which I believe from tonight's test worked a little better. After I do a little code reorganization, which may take me a day or so, I need to divide up the classes. I'm into modularizing my code for this stuff so it doesn't get out of hand and it's more organized. So I'm going to go ahead and do that. I think it works pretty well. It built and I got it debugged in a few hours, and it seems to work very well. It's in terms of the functionality, it's pretty much the same as it was. In terms of the implementation, it's quite a significant change, as you'll see when I push these commits. It's Friday, so everyone have a good weekend, and I'll see you next time.